Hello, welcome back. Lecture 44 today, and we shall continue our discussion on bipolar devices. If you recall, in the last lecture we talked about the Ebers-Moll model, the Kirk effect, and the physics of common base and common emitter junction. We talked briefly about the base transit time and how it, how you can minimize it by using a graded compositional grading in the base, for instance. And so today we will start off our discussion with small signal model and continue from there. Okay. So over to the whiteboard here. So today we are going to talk about small signal model, and we are talking about general BJT here, okay, but the concepts remain similar for HBT also. So I have a base, for instance, okay, and then I have an emitter here, okay, this is the emitter, for instance, and then I have collector here, okay. Now between the base and the emitter there is a base emitter capacitance, which is, I will call it C of pi, okay, and I will ignore all the parasitic resistances capacitances here, okay. So this base emitter capacitance actually has two components. One is your junction capacitance, okay, which forms, although it is a forward bias junction, you will have still have a small depletion region, so that could give rise to a junction capacitance, and the major chunk is actually the diffusion capacitance, which I will call JCDE. So this is the diffusion capacitance because base emitter junction is forward biased, so there will be minority carrier charge storage, and that gives rise to diffusion capacitance. Alright. Now between the base and collector you have what I call C mu, and C mu is nothing but your base collector capacitance. So I can call it the depletion of base collector, the base collector width that will change with applied collector bias, that is your base collector capacitance. Now between the base and the emitter, which is the input, right, you have an input resistance, I call it R of pi, and this R of pi is your input resistance, okay, input resistance, and I can say that this R of pi is equal to actually the rate of change of input current with respect to the input voltage inverse, okay. Essentially how is the input current, which is the base current, changing with respect to the input voltage, which is your base emitter voltage, and if you do that you will find that this comes out to be kT by Q times IB. KT is the thermal constant, and this comes out to be beta naught by Gm, okay, where essentially I am using the concept that beta naught, which is the static gain, is IC by IB. So I am replacing IB here by beta naught by actually IC by beta naught, okay, and I am replacing KT by QIC by Gm, okay. So that is how it is the ratio of the gain by transconductance, which is your input resistance, okay, this is the input resistance. Alright. Then you have an output resistance between the emitter, the collector and the input, the collector and the emitter, and we call them R naught, okay, that is your output resistance, and your output resistance is of course given by the output current, which is the collector current, with respect to the output voltage, which is your collector emitter voltage inverse, and if you do the math it will come out to be the early voltage divided by the collector current, okay. You want the output resistance to be infinity, as large as possible, which means you want the early voltage to be also infinitely large. I mean that means that your output characteristics do not exhibit any output conductance, you do not have any slope in the output characteristic, that is all it means, okay, and that gives you high gain. So you want that kind of R naught, very high R naught, and of course you have between the collector and the emitter you have this current that flows, okay, and that current is basically your Gm times the input voltage, much like the FET, where Gm VGS we call it Gm VBE. So that is your basically the output current that is flowing here. Just remember that whenever I am using capital VCE, it means that the DC bias I am applying, and a small symbol here, for instance VBE, it means the small signal that I am riding between the base and the emitter, it is the small signal base emitter voltage, okay. Just keep it just to keep the demarcation clear, anything that is small, for instance IB is the small signal base current, IC is the small signal collector current, okay. So that is the nomenclature we are using here. Now the Gm for this of course we know that it is defined by the collector current, which is the output, divided by the input voltage, which is VBE. Now if there is, and as you can see in this very simple small signal model, there are no parasitic resistances that I am including or parasitic capacitances that I am including. So the true junction values, capacitance for instance, is the value that I am writing it here, okay. So but in case I am going to include some parasitic components, then I will use the term dash. So VBE dash will be the true base emitter junction voltage, which is different from the base emitter junction voltage VB that I am going to apply. I am going to apply VB as a base emitter voltage, but some of them will be dropping across the parasitic resistances. So, the actual base emitter junction will be seeing something lower, and that I am calling it VB dash. Similarly, VCE dash. Okay. In this intrinsic model that I discussed just now, VBE for instance is V equal to VBE dash, because everything that I am applying on the external terminal is literally the voltage that is dropping on the junction, because I am ignoring all the parasitics. Okay. So, just to keep that in mind. Now, this is the intrinsic model. Now, if I go ahead and say that, okay, what if I include some parasitic components? Okay. What if I include some parasitic components? Let me switch the slide here. Yeah. So, if I include some parasitic components, then what will happen? So, this is your base. So, now the base will have some base resistance, which is R of B. Okay. And then you have C pi, then you have the emitter here. Okay. The emitter here. You also have C mu, which is your base collector capacitance, which is not going to be affected, but then you have a collector resistance, parasitic resistance here. Okay. Then you have of course GM VBE, but here it will be GM VBE divided by 1 plus GM RE. I will come to that. Okay. It is just like FET, the expression actually. This is the current that is flowing, and now here actually I can erase this, and I can maybe I will erase here. Okay. So, okay. So, I can say that this emitter will have its own emitter resistance R of E, because that is the parasitic external resistance that is dropping at the emitter contact. It will always have some finite value. Okay. So, this is your the base emitter capacitance is connected here with the emitter resistance, and then you have your output resistance R naught that we discussed anyways. Okay. And then you have this input resistance, which is R pi, but it is not R pi, just it is R pi into 1 plus GM RE. I will talk about that. Okay. So, this is your small signal model taking into account the external resistances RB, RC and RE. I am ignoring any other parasitic capacitances that might arise because of bond wires or pads or substrate collector coupling. We are ignoring that, but and so this expression of the input capacitance and the base collector capacitance stays the same, but they are not affected by these parasitic resistances as much. However, we will have to derive some of the expressions again, because now we have some parasitic components here. Okay. So, for the first, to start with, the voltage that you are applying in the collector VC, okay, the true voltage that will appear across the intrinsic collector is not equal to VC. This is the applied voltage. Okay. In the absence of parasitics, this is the true collector voltage at the collector terminal, okay, in the intrinsic device. But in reality, because of the parasitic resistances, you will have to drop some voltage, that is your IC times RC. That is the extra voltage you are dropping on the collector resistance, which is this, correct. Similarly, you have a VB dash, the true voltage across the base terminal will be the applied base voltage minus IB times RB. Okay. So, RB will include all the components of the base resistances, just to make it simple. And so, similarly VE dash will be equal to the applied emitter voltage minus it will be IE times RE, but I can write IE, the addition of IC plus IB plus IE has to be 0 for current conservation. So, essentially I can write this as VE plus IB plus IC into RE. Okay. So, then I can write the VBE dash, okay, with some manipulation of the algebraic expressions. It will come out to be an expression something like the true base emitter voltage minus IC RE, okay, plus IB into RB plus RE. Okay. This is the extra voltage that is dropping the emitter, the base resistances, okay, the parasitic resistances. Similarly, I can write VCE dash also, okay, and that will come out to be VCE, that is applied, minus IC into RE plus RC, okay, and you are ignoring IB here in comparison to IC. Okay. Now, using the same using these expressions, if I go on to derive the intrinsic GM, this is the true GM that you should have, the true GM that you have, but what you measure is actually GM. what you measure is GM, but the true GM is this. So then this will come out to be GM divided by 1 plus GM into R of E. R of E is the your emitter resistance. This looks very similar to in a transistor, in a lateral field effect transistor. If you remember, we had GM divided by 1 plus RS into GM for an FET. This RS was the source excess resistance, remember, and similarly here this is the emitter resistance, because the emitter is behaving like a source here anyway. Okay, I am talking about common emitter configuration. So it is very similar to that, and the way you get this expression is, of course, you start off with DIC by dVBE, okay, and then you basically this dVBE, if you remember, this dVBE had this mega expression, right. So you plug in that expression, do some algebraic manipulation, do some assumptions, and you get this expression, okay. So that is there. Similarly, the input resistance R pi will be equal to IB divided by with respect to VBE inverse, and this will come out to be the R pi, that the actual R pi that you are measuring, 1 plus GM RE plus RB by plus RC, okay, it comes out to be like that. And similarly R naught, the output resistance, will come out to be dash, the true output resistance is the measured output resistance plus RE plus RC, okay. So this is actually the intrinsic output resistance, plus this components will give you the measured output resistance, okay. The device capacitance components are still the same because C mu and C pi will remain the same. They depend on the expressions that I wrote down earlier, they will just be the same, okay. So then this is basically about the small signal model, which essentially the extrinsic resistance is considered. And one note of what that I already told you is that the diffusion capacitance between the base and the emitter, if you forgot, in the last lecture we did mention this is equal to GM times the transit time, okay, the transit time. And so this, as you can see, that this diffusion capacitance will keep increasing if your current density IC is also increased, because IC and GM are correlated. Your transconductance will keep increasing as your collector current or the output current keeps increasing, and that is a very interesting concept, because it means that your diffusion capacitance keeps increasing as you keep increasing the IC, okay, and this is ignoring the base width modulation, okay. So increasing the diffusion capacitance can actually reduce your delay time. However, increasing the IC can also charge and discharge the capacitance faster, that is why you try to reduce the delay time. So these are like contradictory goals, so there is always a design trade off that comes into picture anyways, okay. So if you this is precisely what I have written down here. This is called the hybrid pi model, this model that I discussed here, this is called the hybrid pi model, okay, hybrid pi model in BJT, and this was the Ebers-Moll model, that is equivalent circuit for Ebers-Moll that I discussed in the last lecture. So these expressions that I already derived, you can just go through the slides again in case there is some more questions. And finally we come to the derivation of cutoff frequency, which is again very similar to that in transit and FETs. Basically here this is the small signal model including some parasitics also, RB for instance, okay, but I am ignoring the collector and the emitter resistances here. Now if you look at the current that is flowing here, and the voltage that is between this point and this point is V of pi, and you can see that there are two impedances, one is this and one is this, okay. So the parallel of them will be like R of pi into 1 of j omega c pi divided by R of pi plus 1 by j omega c of pi. If you do that, this is the total resistance, or you can say impedance between this point x and this point y. So if you do that, you will get some value, and you divide the voltage dV pi by that total impedance that you get, then you get the base current, which is precisely this, okay. Then the collector current, you see collector current is coming here and some current is flowing here. This current that is flowing is GM V pi, because the voltage between this and this terminal is V pi, this x and y, sorry, this is x also, x and y is V pi. So GM V pi is the current that is flowing here, some current is flowing here, some current Ix is flowing here. So you can say that this component GM V pi minus this Ix is equal to IC. Now what is Ix? Ix is nothing but actually your V pi divided by this impedance here, if I ignore this, okay. So that will be divided by 1 by j omega c mu, that is equal to j omega c mu into V pi, that is what is going to happen. So your IC will be equal to GM minus j omega c mu v pi. This is precisely what is written here. So, you can take the ratio of both of them and you can say that the GM is much larger than this component. This is an assumption. Do some math, you find this expression which looks very similar to the FET expression GM by CGD plus CGS, remember, into 2 pi. Okay, it looks very similar. It ignores some other parasitics, but if you include them it will become slightly more complicated equation, but the basic essence stays the same. It looks very similar in form and structure as an FET, as a field effect transistor. Okay, this is your cutoff frequency for BJT. So, as you know that to increase the cutoff frequency you have to make the GM higher. Good thing is that with increasing collector current your GM becomes higher, which is not the case in an FET. With increasing ID your GM does not become higher, it just shoots up and comes down, and then your capacitances have to be reduced, and that is very fundamental, we know that. Okay. Alright, now we will discuss some few points, and you do not find some of these things very well in most of the textbooks. So, it is very important here. Okay. Beta is of course the current gain, we talk about that in common base configuration typically when you have input as the IB common emitter, actually when you have the in common emitter your input is base current and your output is collector current. So, the ratio between them is beta. So, this figure what it's showing here, and things will become clear when you talk about S parameter, of course. It's showing you the gain in a way, okay, the small signal gain, and it's showing you the frequency here. The reason gain looks very weird here, there is something called H21, that's actually gain. Okay, and if you take the modulus of that and 20 log, you are just plotting that in the log scale, it's the dB. Okay, dB, the decibel you are talking about. So, H21 is the gain because H21 is a form of a matrix which is called the H parameters. Okay, we will come to that later in a later part of the course. H parameters are like 2-port network parameters, there are many parameters, there are Z parameters, S parameters, Y parameters, H parameters, ABCD parameters, different parameters are there, and these are, you can think of these as matrices which are used to describe, characterize and understand microwave circuits, 2-port network specifically, when you have an input port and an output port, and the way the waves go in and then reflect and then get transmitted, etc., can be quantified, can be understood with the help of these different matrices. They have different uses. For instance, experimentally you are going to measure S parameters, but then the gain is given by H parameter, it is easier to visualize that way. However, going from S to H is not very trivial. You have to go to Z parameter, and then you have to come to Y parameter, then you have to go to H parameter because of certain ways. You have to de-embed the parasitics, you have to remove the parasitic component. We will all come to that in the subsequent part of the course, but the bottom line here is that Y axis represents gain, and you can see that gain stays flat at very low frequencies, and then at one point it will start to fall down. Typically the rate at which it falls down, the slope at which it falls down is 20 dB per decade, which means the gain will fall down by amount of 20 dB. It will fall, the gain will fall by 20 dB for 1 decade. What does 1 decade mean? 1 decade means 10 times change in the frequency. If I go from say 1 gigahertz to 10 gigahertz, 1 gigahertz to 10 gigahertz, that is 1 decade. Okay, 10 gigahertz to 100 gigahertz is another decade. So, between 1 gigahertz to 10 gigahertz my gain will fall off by 20 dB. From 10 gigahertz to 100 gigahertz my gain will fall off by 20 dB. That is ideal. I mean, in realistically certain components can actually make it slightly more or less in way, but 20 dB per decade is like the standard, it is how it falls. And in the control theories, of course you can say that it has hit a pole. If you remember your undergrad electrical and controls classes, you have poles and zeros. So, we say that it has hit a pole okay, in the transfer function, and so it has started falling off at 20 dB per decade slope. What is the physical underlying understanding? The underlying physics or the understanding is that your gain that you get, which is essentially output by input, it falls off with frequency. Why? Because as you increase the frequency, your carriers have a finite speed. So, as you keep increasing the frequency of the signal, your carriers are not able to catch up with the signal as much. So, as you keep increasing the frequency, the gain that it will offer also falls. The gain at low frequency is very good, but with higher frequency the gain will fall off. Okay, and eventually at one point the gain will become 1. What it means by 1 is that the output is equal to input. That means there is no gain, it is 1, and 20 log of 1 will become 0. So, this quantity will be 0 dB. Okay. So, at 0 dB or 1, a gain of 1, you are talking of the cutoff frequency is called FT, the current small gain, small signal, the current gain cutoff frequency. This is current gain that I am plotting. Okay. Now, with that background in mind, maybe I will remove the annotation here. Okay. With that background in mind, you see this corner frequency here, which is some f of beta, Now beta that we typically define is actually beta naught, which is your DC, it is your static. In your DC measurement you have a collector current, you have a base current, and you define the ratio as the beta. However, in small signal, in RF, where you have a high frequency signal coming in, we do not talk about the static beta, although static beta is very important. We talk about the beta in a real context, we talk about the gain H21, and this value that stays flat at very low frequency is like your static beta. Okay. The gain is 20 log beta naught. Okay. And as it hits a pole, we call that frequency as say f of beta. At that point it starts dropping by 20 dB per decade. This beta, the static beta, is also very critical, by the way. Okay. It is very important because it helps you to understand the biasing, how you will bias the device. It also helps for low noise, a high beta, static beta naught is very important. Just because we are dealing with RF signal at high frequency does not mean the static beta is less important. Okay. It is very important. However, this beta will depend on many things, as I said, the base width, the base width will keep changing as with collector base bias. It depends on recombination lifetime, the doping in the base, that also depends on doping in the base. So many factors can affect the beta. So if you design a circuit with the exact value of beta, it may be dangerous because the beta can depend on so many process parameters, so many device fabrication parameters. So the people who design RF circuit in a BJT or HBT typically, they typically design such that the design is insensitive to beta, as long as beta is good. Beta can be more than 20, for instance, need not be always 50. Beta is more than 20, say 25 or 30 is good enough. As long as beta is more than 20, my circuit design holds true. It is not very sensitive to beta. Okay. So that we have to keep in mind, because the circuit designer cannot rely on accurate value of beta, it can change. Okay. And most circuits will operate in this range. You do not want to operate near the cutoff frequency because your gain will be typically almost 0. Okay, I mean 0 dB. So you typically operate somewhere here, so that you are getting some decent gain, but you are also operating in the regime where the gain is falling with frequency. Okay. And of course this point that I call it hits a pole, we call it a low frequency asymptote, single pole roll off, that is it's falling off with 20 dB per decade fall. Okay. So just to give you a context, this is also, the concept is very similar also in your FET, except that we do not call it a beta there, but in a BJT we have a static beta concept here. But the 20 dB per decade roll off is also, it also holds true in lateral field effect transistors also because of hitting the pole. And again in FETs also people try to operate the device somewhere around this point, where you are on the downward slope, but you are taking a regime where the gain is reasonably high. You need reasonably high gain. You typically have the circuit designed at least a few times lower than the cutoff frequency. Okay. So just please keep that in mind. Now that is with respect to frequency, the gain with respect to frequency. Now in this plot you see the cutoff frequency Ft. Here is on the y axis, the cutoff frequency is on the y axis, and on the x axis I have the output current, IC, the collector current is like the drain current in FET, but the physics is very different. So ideally with increasing collector current, your RC delays become lower because the collector current can charge and discharge the capacitances very fast. That is the reason why people try to operate the BJTs at high collector current, because it can charge and discharge the capacitances very fast. Also higher IC gives rise to a higher GM, because GM and IC are directly proportional. So higher gain and a lower RC delay helps the device in many respects. That is why people operate it at a higher collector current. So with higher collector current, as you keep increasing the collector current, your FT also keeps increasing like that, and eventually ideally the FT should flatten out, because this part is where you have basically charged and discharged capacitances to the maximum limit that you can. In this regime your charging and discharging capacitances do not matter, because at this point you have the base transit. Okay. The base transit, the base electrons will take some time, certain time to travel across the base, and to a first order that is given by the base width, the neutral base width square divided by 2 times the diffusion coefficient of electrons in the p-type base. This quantities does not depend as much on the collector current, because this is not a charging or discharging of the capacitance. This is the electrons physically traveling across the base. It is like the, I mean it helps, higher collector current definitely helps, but there is a base transit time also. Okay. And actually there is another component here which I have not written so far, and that is a smaller component, but that is still important at very high collector current densities, which is your base thickness, which is WBN divided by VSAT. Vsat is basically the velocity of saturation, which is the maximum velocity with which electrons can travel. This is typically like they call it tau exit, like when the electrons exit from the base towards the base collector depletion, that exit velocity is the saturation velocity, then base width divided by that gives you it one part of the base transit time. So both of these combine actually give you the total base transit time, and this is insensitive as much to the collector current actually, okay, it is insensitive to the collector current, and so this part is constant. So ideally, okay, so ideally you should have gotten a higher cutoff frequency and then it should saturate out. However, in reality it just falls off like that, and this part is because of high injection or the Kirk effect that we already talked about. We do not have to discuss it again further. Kirk effect is that your base there is a base push out, your base width has increased because your holes from the base are spilling over to the collector side. Why? Because the electric field at the base collector depletion region has disappeared because of the Kirk effect, which we already talked about, right. So although high current is required for a good FT and higher GM, but eventually the high injection effect will lower the cutoff frequency. This is your sweet spot where you essentially want to operate. You do not want to degrade the cutoff frequency at higher injection current, okay. You have to understand that cutoff frequency is not the only golden figure. There are many factors, F max for instance, there is also breakdown voltage, GM, everything is there, and noise, linearity, power, many things are to be looked at the power amplifier or the low noise amplifier point of view. So FT is not the only parameter, but this is just a snapshot to show that how FT varies with the cutoff with the injection current, okay. So this is fine, and like FETs, not only BJT, FET not only should have high cutoff frequency, but their overall parasitics have to be low, breakdown has to be good, there are thermal issues, there are many issues that we have been talking about in the context of FET. Most of them holds true also for BJTs in a way, except the fact that with higher collector current you increase the FT and increase the GM to a certain extent, which is not the case in FET, okay. So with that I will conclude lectures 44 here today, and what we have discussed today is we started off with small signal model, both intrinsic and extrinsic hybrid pi model. We understood the cutoff frequency and a few points, critical points on the DC static gain and the high frequency gain beta, how it falls off with higher frequencies, and then we concluded with a discussion on the cutoff frequency with respect to the higher collector current and why higher collector current is useful in an RF BJT or bipolar device, okay. So thank you for your time. I will see you next class, lecture 45.